Hi, Sabine.
Bob.
How are you?
I'm good. How are you?
I'm pretty good. How did I do with pronouncing your first name?
That was okay.
Better than the average American? That's all I'm asking for.
Yeah.
Thank you. Thank you. Let me introduce this. I'm Robert Wright. This is The Wright Show, available on both streaming video and via audio podcast. You are Sabine Hossenfelder, research fellow at the Frankfurt Institute for Advanced Studies. You've written a very interesting book called Lost in Math: How Beauty Leads Physics Astray. It's about the role of aesthetic judgment in developing theories and in becoming committed to theories. And it's a critique of the role that aesthetic judgment plays, I think it's fair to say. And, you know, to give people a sense for the breadth of the critique of physics that is implied by the book, I want to actually read, not from the book, but from your blog, which is Backreaction, one word. I think this is a recent post. It's called The Present Phase of Stagnation in the Foundations of Physics is Not Normal. You write, nothing is moving in the foundations of physics. One experiment after the other is returning null results. No new particles, no new dimensions, no new symmetries. Then you go on to say, some have called it a crisis, but I don't think crisis describes the current situation well. Crisis is so optimistic. It raises the impression that theorists realize the errors of their ways, that change is on the way, that they are waking up now and will abandon their flawed methodology. But I see no awakening. The self-reflection in the community is zero, zilch, nada. They just keep doing what they've been doing for 40 years, blathering about naturalness and multiverses and shifting their, quote, predictions once again to the next larger particle collider. So I think people have a sense that you're not entirely happy with the state of physics. It's, I guess maybe let me first ask, how are you being received by fellow physicists? I might read that and think you don't have a lot of friends, but maybe I'm wrong.
Well, you're overgeneralizing this. I'm writing particularly about the foundations of physics. So that's a part of physics, but physics is much larger. You know, there are a lot of other disciplines like atomic and nuclear physics, optics, quantum information, astrophysics, all that kind of stuff, where I would say things are going okay, largely. So I'm really concerned only with the foundations of physics. And now you ask, well, how have I been received? I have basically gotten no response from people in the fields that I've written about. I have gotten a lot of feedback from physicists in other disciplines, largely to tell me that they are happy that I said it because they always thought so.
Okay, and by foundations of physics, we mean things like the quest to unify the four forces, right? Like a grand unification theory would be an example of progress at the foundational level.
Yes, that's one of the fields that is implied here. So largely speaking, I mean those areas of physics that are concerned with reality on the most fundamental level. So, you know, we're all reductionists down here. So that basically means on the shortest scales. So yes, that's high energy particle physics. And so this quest for the unification of the forces plays a big role. It's also the search for a theory of quantum gravity. So that's basically how the quantum nature of space and time is supposed to work. And I also include the foundations of quantum mechanics itself. And to some extent, cosmology. So this question like, how did the universe start? Where do we come from? All that stuff.
Okay. And so now there's a theory you don't spend much time on in the book, but a lot of people have heard of it. It may be useful to talk about it a little. It's string theory. Does that count as foundational?
That's a tricky question. So string theory was originally not invented as a theory that was supposed to revolutionize the foundations, but it was supposed to be a theory for the strong nuclear force, which is now been taken over by quantum chromodynamics. But it was then indeed proposed as a theory for grand unification plus quantum gravity. So that's solidly foundations of physics. Now, in the past 15, 20 years, things have been shifting back to not foundational stuff, in particular condensed matter physics. So there's a part of string theory that is no longer concerned with the foundations of physics. But that's not the part that I'm talking about in the book, right? So I'm talking about this quest for the theory of everything.
Right. And string theory, I think, is an example of kind of aesthetic judgment playing an important role, right? Because it's a theory that hasn't yet been tested successfully or really tested at all, maybe. So it hasn't yielded, it hasn't been confirmed experimentally, but some people are committed to it, and they're committed to it for reasons that I think you would call, at least in part, aesthetic, right? I mean, we should say that maybe, so the idea, as I understand it, of string theory is that, like, well, you've got all these different particles, you've got like 25 different particles, but maybe there's something simpler underneath. There's just like strings, and it's all like one kind of string, but the strings have different vibrations, and depending on the frequency of vibration, and I may be getting metaphorical here, and this probably is not technically precise, but the basic idea is maybe different vibrations are what we think of as actually different, qualitatively different particles, right? So, I mean, you can correct me if that's fundamentally wrong, but the thing I'm trying to get across is, like, there's an appeal here because, oh, wouldn't it be, like, beautiful if things were so simple, and this complexity could be reduced to this simplicity. So this is an example of a role of aesthetic judgment in commitment to a theory. Is that right?
Yes.
And
so string theory is seen as a theory that is very elegant. For one, because as you just said, it's a very simple idea, right? Everything's made of strings. So there, I've said it. And then if you try to actually go and formulate it mathematically, it turns out that the theory has its own will. You know, it will not let you actually do everything that you can think of, but it will tell you, for example, that the world needs to have 6 additional dimensions of space. You need to have supersymmetry, and it goes on like this. And this is what physicists like to call an elegant theory, because it brings you to some surprising insight. So it's not only simple, it does things for you. And so I think that a lot of physicists consider this to be very convincing. And I will admit that at the time when people started talking about this, so this was in the 80s, it must have been very, very convincing, because it seemed like the obvious next thing to do, right? They had the standard model and they had general relativity, and now what was missing was a combination of the both. And it looked like string theory would be able to do it. It's just that it didn't work out.
Yeah. And there's one issue that arises here that maybe isn't central to your argument, but as long as we're talking about string theory, I want to mention it, which is like, simple in what sense? So in other words, yes, it would in one sense simplify things that there was just like one kind of string instead of 25 particles. But on the other hand, if you've got to add like a bunch of dimensions to the world, right? It's like, I can handle 3, maybe 4 dimensions. But if part of this new theory that is in one sense simpler, like adds a bunch of dimensions to the world, which is something I can't even conceive of, in what sense have you on balance simplified things?
Well, the simplification that theoretical physicists like to talk about is the simplification of the assumptions that enter the theory. So take this example with the dimensions. As I just told you, once you start with the idea that everything is made of strings, the theory will actually tell you what the number of dimensions is. So this is not an additional assumption.
No, it's not an assumption, but it's a complexification.
Yeah, so
of reality. Well, I thought the goal was simplicity. That's what I'm saying.
But it's, as I said, it's complicity in terms of the assumptions that you start with. that you get out complex conclusions. That's an entirely different thing. That's totally okay.
Well, wait, but the ideal is, I thought, in science is that you explain in simple terms observed complexity. So the theory of natural selection is a good example. All this biological complexity, and you account for it with a theory that's actually very simple to explain, but that was complexity you observed in the first place. If the theory adds complexity to the claims about reality, like it's not like we didn't know there were 10 dimensions that needed to be explained before string theory came along, right? So if string theory comes along and says we can explain 10 dimensions, I'm like, wait a second, we didn't ask you to do that. We don't even know, you're the only person telling us there are 10 dimensions. Do you understand my objection?
No, what I'm saying is, sorry, you start with the idea that everything is made of strings. You arrive at the conclusion that the universe has 10 dimensions. So that in and by itself is not adding complexity. Where it starts becoming difficult is if you then notice, well, actually, we haven't seen 6 of these dimensions. And then you have to come up with a way to make 6 of them go away. Okay, that's when things start getting...
Well, has that happened?
Well, that's where you have to start adding assumptions to the theory. So you start simply with this idea, everything's made of strings. Okay, so now the theory tells you, well, you need these extra dimensions, you need supersymmetry. Problem is, we have seen neither the extra dimensions nor supersymmetry. So now you have to start adding assumptions to make these troublesome things go away. And that's where it starts becoming less simple. Right.
Okay.
So I guess you're right in a sense, but I think that's not how string theorists would see it.
No, clearly. That's the problem. So let's back into your own exploration of the concept of beauty as physicists use it by making clear one thing you're not saying, one thing you're not objecting to. So there is this thing called Occam's razor. Like if two theories both are capable of explaining a phenomenon, presumably a phenomenon of some complexity, but in any event, and one of them is simpler than the other, we go with the simpler theory. Now, that is sometimes casually talked about as the more beautiful theory or the more elegant theory. I've heard those terms used that way, but we should be clear, you're not, before we get into what you mean by beauty and physicists mean by it, you're not objecting to Occam's razor, right?
No, that's not the simplicity that I talk about. So Occam's razor is a good scientific criterion. It's not quite as simple as you made it sound because, you can always get a theory that works parametrically, so that is parametrically more precise by making it a little bit more complicated. So you usually have a trade-off between having a theory that is simpler and a theory that is more accurate. And then you have to use some statistical tools to find what's the optimum, and there are different ways to do it. But yeah, roughly speaking, that's how it works. But that's not the criterion from simplicity that physicists are actually using in the foundation. So what they want is an absolute simplicity. You want a theory that is simple, period. Mm-hmm. Like a good example is the unification of the forces that you were already talking about. So we have this standard model of particle physics with the 25 particles, and it has 3 different forces. That's electromagnetism and the 2 nuclear forces, the strong and the weak. But physicists would prefer if there was only one unified force, because that would be simpler, right? And so it would be in an absolute way simpler. And what I'm saying is that, that would be all well and fine, and I can understand the aesthetic appeal, I would also find this nice, but there's just no reason why nature should be working this way.
Well, I guess the reply from a lot of scientists would be, actually, so far, the assumption that we can reduce complexity to simple explanation has turned out to be true. It has turned out that nature works that way in the sense that, for example, at one point we thought of electricity and magnetism as these 2 different things, but no, we found that they can both be reduced to the electromagnetic force and so on. Or back to Darwin, at one point we had no idea were these things all separately created or what. Oh no, there's a single theory. So in a lot of cases, or get back to Newton's theory, right? It's like, why are these bits of light in the sky going all these different places? Well, you have a very simple theory that not only explains that, but explains why stuff falls on Earth and so on. So I think they would say, well, so far, it has been the case that if we push hard enough, we do tend to find that beneath complexity, nature is concealing kind of simplicity of explanation that can be uncovered, right? I mean, don't you think we have gotten a lot of positive reinforcement for the assumption of simplicity?
Yes. So one thing is, from the examples that you just named, you have been confusing the relative with the absolute simplicity, in particular in reference to Newton. But yeah, it's certainly the case that there are historical examples where the strive for absolute simplicity has been useful. Electromagnetism is an example. And that's also why I think it was a good idea to try to continue this after the development of the Standard Model. But the point is, it did not work. And there is no deeper reason why it should continue to work. So one thing, for example, that you conveniently left out is if you start at larger scales, you know, not at the scale of chemistry or something, but with even larger things, like, say, the scale of planets. If you go to smaller scales, then things start getting more complicated, because you have all these, humans crawling around and their social systems, and it's a terribly complex system that actually we do not have a good mathematical formulation for. And it's only if you go to even smaller scales, beyond all this biology stuff, that things start getting simpler again. And now you go down to atoms and atomic nuclei and the constituents of the nucleons and so on. And that's where we are now. And now there's the question, what reason do we have to believe that if you go to even smaller scales, it will continue to get simpler? And the answer is, I think we don't know.
Right. Okay, I mean, I would, as an asterisk, I'd add that I don't think it's a general case that as you go to smaller scales, they get more complex. It's true within the system of life. It's true if you're on a planet where there's animals, but so far as we know, there's only one of those, and there certainly aren't many. So, I mean, in the physical universe, kind of out there, so to speak, is it the case that as you get down to smaller scales, things get more complex? I mean, of course, with quantum physics, they start getting weird and hard to conceive, but that's different. I mean, isn't it the case that as you go to smaller scales with inanimate matter, that the simplicity holds? We have these simple theories that account for the motion of the particles and stuff. Isn't that right?
Well, yeah, but you put the conclusion into the assumption by only talking about inanimate matter.
Well, okay, but I mean, life seems to be a pretty rare and narrow subset of reality, so far as I can tell.
It's not that I'm saying that there are little humans inside the nucleons or something like that. I was just using this as an example that there is no metaphysical deeper reason for why these forces should unify. Why should they? If there was a hard mathematical criterion from which we could derive it, then we would derive it, but there isn't one.
Well, not when some people would say not when they've found yet, but okay, so let's get into what beauty means. I mean, as I kind of suggested, I had always thought that actually elegance kind of did refer to Occam's razor, that when people talked about an elegant theory, they mean, oh, look how simple it is and look how much it can explain. But that's, you did some kind of actual anthropology, went and talked to people about what they mean by beauty, physicists and so on. And so you have a different way of putting the matter. So why don't you talk about what physicists seem to mean when they talk about a theory being beautiful?
Yeah, so the reason that I did it was that I didn't just want to go and say, this is what physicists mean when they talk about beauty, because, I might just have been wrong. So I thought I would go around and actually interview some people. And that was an interesting experience because I'd never interviewed anyone before. But yeah, so, and it turned out that when physicists, at least in these disciplines, right, talk about a beauty, they largely agree on what they mean. So simplicity is a very strong part of it. We already talked about this. Then there is this more this vague notion of elegance. So you don't only want your theory to be simple, you also want it to give rise to some surprising insights. And this is what people refer to as elegance. I already mentioned string theory as an example. Another, maybe even better known example is Einstein's theory of general relativity, which is usually perceived as a very elegant theory because not only is it simple, it also gives rise to a lot of surprising conclusions, right? For example, gravitational waves. So this is something which you don't immediately see if you look at the theory, or black holes, wormholes, gravitational lenses, and all that stuff. So it has a lot of...
Let me just to make sure I understand you. So elegance consists of a theory having an implication, right? Like giving rise to an expectation or explanation for something beyond what it was initially intended to explain. Is that it? And something that turns out to actually be there, or is that wrong?
Well, normally if you think of a theory, you're not entirely sure what you intended to explain in the first place, right? So I'm just trying to say that if you derive a theory like Einstein did, say, he would not have known what all the consequences are. Actually, we still don't know, because these equations you can't just solve in a simple way. It's complicated. So only if you study the theory further will you find out what it actually tells you about the world. And so the more surprises the theory has in stock, the more insights you gain from it, the more elegant the theory is being perceived. And of course, that's an entirely subjective notion that also changes over time, which I think is why it's a bad scientific criterion. For example, the electromagnetism, I guess, originally was not considered all that elegant just by the way that it was formulated. It's only much later that people understood the mathematical formulation better and they found a way to phrase it in a more elegant way. And on the other side, what you think is a surprising outcome of a theory depends on how much you already know about it. Right, and that already depends on how much mathematics you know. So I don't think it's scientifically a good criterion. I don't blame anyone for thinking that it's elegant, right? But right. Why use it as a criterion for theory development?
Do you also mean surprising in terms of kind of just like weird stuff, like so wait. We should reconceive gravity as being kind of curvature in the space-time continuum. That's weird. Or quantum physics is weird. You don't mean surprising in terms of just sheer kind of mind-blowing strangeness, do you?
No. So the way that people put it to me is that it gives rise to new connections. So that's a typical way that they would put it. Or the way that the philosopher Richard Darwin put it, he called it unexpected explanatory closure, which I think is basically the same thing, that you have this surprising conclusion that you did not anticipate when you set out working on the theory.
Yeah, fertility is a term that's sometimes used about theories, meaning it gives rise, I guess maybe they mean it gives rise to a lot of other work by a lot of other people, but that's not totally unrelated to this notion of surprise, right? A fertile theory.
Yeah, that's right. It's not totally unrelated. Though theories can also be fertile or fruitful is the way that I usually hear of it for other reasons, because it's simple to make a calculation. That can lead to a lot of output, not necessarily because the theory is so elegant.
Right.
So, supersymmetry is an example for this, right? The original idea is very beautiful and very elegant, but then if you come down to the level where you actually go and make predictions, say, for the Large Hadron Collider, you have to break the symmetry and you have these, 105 parameters or something like that. There's no way you can tell me that this is still elegant. But it's a very, very fruitful theory in the sense that you can do all kinds of calculations for all kinds of cross-section, get your papers published. And certainly the ability to publish a lot of papers makes it look more important.
Yeah, well, that is a fundamental incentive for most working scientists, right? And you think in some ways a corrupting one.
Yeah.
Because for one thing, it leads people to buy into the established model, right? It's like once string theory is a cool thing and it's getting funded and stuff, then there's an incentive to buy into that.
Yeah, there's a very strong incentive because you need to get money, right? You need to have a position funded. So in the fields where people have the money, you will get a position. I mean, it's as simple as this. People go where money goes where people goes. So you get this feedback loop where you get bottles of research, and these are really hard to get rid of once they have reached a certain size.
Right, right. So we've talked about two of the three components of beauty: simplicity, just how simple a theory is, not necessarily compared to other theories, but just like in absolute terms, is it a simple formulation? Then surprisingness, kind of, and then the third is naturalness, right? Do you want to talk about that?
Yes, naturalness is usually the criterion that people find most difficult to understand if they don't have a background in particle physics. What particle physicists mean by naturalness is that if you have a theory and it contains certain parameters that don't have units, so they are just numbers, then these numbers should be close by one. You know, they shouldn't be really large and they shouldn't be really small. They should be kind of just right.
Right.
So
the ratio of the mass of one kind of particle to the mass of another kind of particle, that has no units because the masses cancel each other out, or they're in the numerator and the denominator. That's an example of something where physicists just kind of say, wait, if you've got a ratio of mass between one particle and another that's like 1,000 to 1, I don't like that. That's just too high. That's too high a number. Is that the kind of thing they say?
Yeah, but it's a little bit more complicated than that. So this is this ratio of masses is something that you would call not natural. But in particle physics, they have a more elaborate version of naturalness, which is called technical naturalness. So and that is actually a weaker criterion. So it tells you that some small numbers are allowed, provided that there is a reason for why they are small. And so the ratios of masses in the standard model, they are all technically natural. Except for the mass of the Higgs boson, or since we're talking about dimensionless numbers, it's the mass of the Higgs boson relative to the Planck mass. So that comes out to be 10 to the minus 15 or something like that. And that's a very small number, which is not technically natural. And
so is the Higgs boson a problem then from the point of view of some physicists just because of the number it generates?
Yeah, right.
But they all believe it, right? I mean, its existence was kind of confirmed, right? That's the great triumph of the collider, right? Was to add credence to the existence of the Higgs boson.
Yes, no, I think, basically no one doubts that it actually exists, and the mass has been measured. So we just know that this ratio is 10 to the minus 15. Now, the thing is that if you just have the standard model with the Higgs, then this ratio is technically unnatural. And since physicists don't like this, so this is what they think is unaesthetic. It's not pretty, it's ugly. You don't want this unnatural number there. And this is why they have invented a lot of new particles, because you can use those to explain why this ratio is small. Supersymmetry is an example for this. You can add a new symmetry that basically tells you why two large numbers almost exactly cancel each other, leaving behind this little remainder that gives rise to this small ratio. So supersymmetry does it for you. And this is the reason why so many physicists thought that the Large Hadron Collider should see something else besides the Higgs boson. This was all this argument from technical naturalness. It doesn't necessarily have to be supersymmetric particles. This was just the most popular idea. It could have been something else. But the point was that to save this idea of technical naturalness, you have to find something new close by the Higgs boson, and this just has not happened. So it's out of the window. And now, well, particle physicists, as you read in the book, right, they're confused. They don't know what to do.
Yeah, it seems strange that you would expect ratios to be small, but I guess there's a long track. Nature has a long track record of producing small ratios. Is that it? I mean, I don't. Naturalness is I think you've probably encountered that for lay readers at least, naturalness is the strangest of the three components of beauty as you depict them. Naturalness is the one that's hardest for me to understand, like why it would be an expectation in the first place.
Yeah, so there's an example that I like to give is consider you go for a walk and you see a field of sunflowers. Okay, so you've probably seen fields of sunflowers. Normally the sunflowers are kind of the same height. They might be 1 or 2 meters depending on the kind of sunflower. They kind of have the same size. Now, if you go and you see a field with sunflowers and one of the sunflowers is 1 million meters high, you would say, well, that needs some explanation. And you can convert this into ratios. So this would give you a number of 10 to the minus 6, 7 or something like that. And it's this intuition that physicists bring to the fundamental laws of nature, that if you have a constant there which has a large or small ratio, they think it's unnatural for basically the same reason. Because it looks like there is something weird going on. You know, it looks like a conspiracy. They think it requires an explanation. And now the point that I'm trying to get across in the book is that the reason that you are surprised by this large sunflower is that you've seen a lot of fields. You've seen a lot of sunflowers. So you have a statistic on which to rely on. So your assessment that this is surprising comes from your knowledge. Right? So that's a reasonable assessment. So naturalness is not generally always a bad thing to look at, but it is a bad idea if you use this intuition that you get from your observations of nature for the values of parameters in the fundamental laws of nature, because for those, you do not have any statistics. You cannot have any. We have only this one set of parameters. So the Higgs mass is whatever it is. You know, you can't compare it to the Higgs mass in a lot of other universes.
Right. Well, the other reason I might expect the Higgs boson to have an unusual relationship to other particles is I've heard that it has this. And here's another thing that's completely hard for me to wrap my mind around, but do I recall correctly that the Higgs particle, the Higgs boson, is the thing that gives mass to other particles? That's something that's said about it, right?
Yes, though it's a little bit more complicated than that. So it gives masses to the other particles in the standard model. So there are these 25 fundamental particles, and well, some of them are massless. So it does not give masses to the massless particles, needless to say, but it gives masses to the massive particles. Now, the masses of most of the stuff around us, though, come from energy, basically. So it's binding energy from the nuclear force. So I think a lot of people get this mixed up. But yeah, so you need the Higgs boson to give masses to the fundamental particles in the standard model.
Yeah, well, I can't really wrap my mind around that. It seems kind of strange, but I would certainly think that it's a sufficiently distinctive property so that if the Higgs boson has other distinctive properties, it shouldn't surprise people. But anyway, you're
yes, you're totally right. It's the Higgs boson is different from the other particles in very specific ways that we know, and that's also the reason why the Higgs mass is not technically natural. So these are directly related.
Mm-hmm. So one thing you're saying is that, you know, sometimes you just have to accept things. They're not going to have a deeper explanation. It just is the case that, it may be the case that like, okay, the Higgs boson, you have to accept this quote unnatural ratio involving the Higgs boson. And in trying to kind of explain it with supersymmetry or whatever, you may just be wasting your time, not just because supersymmetry is the wrong explanation. There just may be no explanation, right? Is that what you're saying?
Not exactly. So, I mean, generally, I do believe that if we keep on digging in the foundations of physics, at some point we will come to a level where there just is no deeper explanation, and that's it. But of course, I don't know if we have yet reached this level. So generally, I think it's good to always look for better explanations. The question that I'm concerned with is, where is the best way to look? And I just think obsessing about the mass of the Higgs boson is the wrong place to look. It's just not a good problem.
Yeah. And certainly in the case of the four forces, gravity, electromagnetism, weak nuclear, strong nuclear, if I've got those right. One thing you're suggesting is that may in the end be something you just have to accept. Maybe the universe just isn't any simpler than that, right? That's certainly a distinct possibility in your view.
Well, we do know that we kind of have to get together the standard model with gravity. And so this is actually a hard mathematical problem. So there's this question, where's the theory of quantum gravity? That actually string theory tries to solve. So string theory is actually solving a good problem. What I'm not so sure about is this unification of the other three interactions. Maybe they're just three and they're just sitting together there. And yeah, they would be ugly, but so what? But when it comes to quantum gravity, the thing is that the theories that we currently have, they have internal contradictions. And we know that this cannot be how nature works. There has to be a solution for that. And this is this theory that's called quantum gravity that everyone is looking for. Actually, this is a problem that has been known since the 1930s. So It's not exactly new, but there's not a lot of progress that has been made on it.
Okay, so there are these three forces within the standard model. Electromagnetism, weak nuclear, strong nuclear, and then there's this fourth thing, gravity, that's kind of qualitatively different. And you're saying that those three may never be united, but you actually have a strong expectation that gravity does need to be unified with the standard model, which those three kind of constitute. What's the basis? Why is your expectation strong in one case but not in the other? Why is it so clear to you that gravity will be, if I'm understanding you correctly, will be ultimately unified with the standard model, those three?
Well, it has to be because, the particles in the standard model, as you just said, they have masses. They also have energies. And we do know that masses and energies create a gravitational pull, or if you want to put it in Einstein's terms, they create a curvature of space-time. Now, the issue is that all these particles in the standard model, they have quantum properties. They obey Heisenberg's uncertainty principle. They can be in what's called a quantum superposition. That's when you have a particle that can be in two places at once, can be here or there at the same time. That's the weird point about quantum mechanics. And now you can ask the question, suppose I have a particle that is in two places at once, where does the gravitational pull go? Yeah, so the thing is that Einstein's theory of general relativity cannot answer this question because it does not have quantum properties. But we know that there has to be an answer because nature can do it, right? Where does the damn gravitational pull go? The thing is that we can't measure it. So we cannot just take an electron and put it in so we can put the electron in a quantum superposition, but then the gravitational field is so weak that we cannot measure it. But it has to go somewhere, right? And that's what we need a theory for.
I guess my intuition would have been to say, like, okay, of course, one way to look at it is like the particle is in two different places at once. Another way to look at it is there's a probability distribution about where the particle will be found when you actually measure it, and that's kind of spread across a number of possibilities. And maybe if you assign, like, gravitation in proportion to the probability that the particle is in any given place. Have I come up with a new theory that's gonna get me the Nobel Prize? I mean,
no.
This could be a big. No, wait, don't. This could be a big moment for me. I don't want you to ruin it right away. I just want to revel in the possibility that I'm going to win the Nobel Prize. Now, tell me. Am I?
No, probably not. So what you just mentioned is what's called semi-classical gravity. This is when you only couple the expectation value to the source of gravity. This is what we do all the time. That's a very good approximation. That's basically why we can use Einstein's theory of general relativity to begin with. We can just ignore these quantum effects and only take the probability distribution. The problem is, what do you do with the measurement? Because we know that when you make a measurement, you have to, at least in the Copenhagen interpretation, you have to update the probability distribution. And that's, for all we know, an instantaneous update. But you cannot do such an instantaneous update in Einstein's theory of general relativity, because everything has to move slower than the speed of light. And that brings you into this whole conundrum with, well, what actually is the quantum measurement?
Yeah.
Yeah, right. There are also other reasons why this doesn't work, but I think this is the most obvious one. So it's not that simple.
Yeah, so I'm sorry to hear that. What about quantum physics generally? Where does that fit into this whole like beauty thing? Because I would think, I mean, the most distinctive aesthetic property of quantum physics is weirdness. Difficulty wrapping your mind around it. I mean, you've pointed to one particular thing that's hard to conceive, a simultaneous location of a particle in two different places. But how does that? I mean, some like Einstein kind of said, no, it's too ugly, right? I mean, he resisted quantum physics in a certain sense on aesthetic grounds, right?
I'm not sure. I haven't seen any quote from Einstein where he was actually complaining that it's unaesthetic. I think he didn't see it as a finished theory because he felt that so quantum mechanics is not deterministic, right? So you cannot actually calculate the outcome of single experiments. You can only calculate the probability. And Einstein just felt that there has to be an underlying theory in which you could, in principle, calculate the outcomes. It's just that we would need to have more knowledge, which we don't have. So these are these hidden variables that people keep talking about. I'm not aware that he actually thought it's ugly. He just thought it was not the last word, but it has remained the last word. So the reason that I go on about this in my book is that there are other people who have this argument that we have to change something about it because it's ugly. And I personally don't think it's an ugly theory. I actually think the mathematics is pretty, but maybe I'm odd. So there are definitely people who think that, for example, these quantum superpositions and this whole non-locality thing is ugly and has to go away. And I don't subscribe to this, but this has certainly created a lot of research.
Yeah, okay. Now, so we've mentioned grand unification theory, the quest for grand unification theory. You're suggesting that possibly too much time is being spent on that precisely because people are being misled, in part at least because people are being misled by the emphasis on beauty. It would be beautiful if it were true, but we're spending a lot of time trying to find it. And you're saying it may not be there. A couple of other things you mentioned that a lot is invested in on grounds of beauty, I think, that may turn out to be lost causes. One is supersymmetry. We mentioned that. Another is the multiverse, right? What can you talk about what the multiverse is? That's not the same as the many worlds interpretation of quantum physics, right? The multiverse.
The many worlds interpretation is usually thought of as a specific type of multiverse, but there are other multiverses. For example, we already talked earlier about string theory, right? So string theory gives you these additional 6 dimensions that you somehow have to get rid of. Now the thing is that there are many ways to get rid of these dimensions, so it creates a huge number of different theories, actually. And these populate what is known as the string theory landscape. Because the problem that string theorists ran into was that they were thinking that this theory is like the final theory, right? It's the theory of everything. It's supposed to explain everything. Now, if it turns out that because of this issue of getting rid of the dimensions, there are actually a lot of different theories, but it's the final explanation, then you have to accept that they are all equally real, right? Because if you add another criterion that says, well, there are an almost infinite number of them do not exist for reasons I don't know, then it was not the final theory. So That's the string theory landscape. So that's a particular type of multiverse. Then there is another type of multiverse that is called eternal inflation, where basically the Big Bang that caused our universe happens an infinite number of times, continues to happen everywhere. So there are all kinds of universes created all the time, and presumably will go on forever. And then you can combine all these multiverses in different ways. You can lump together the many worlds of quantum mechanics with the string theory landscape and with eternal inflation. And then there's Max Tegmark with his mathematical multiverse, the mathematical universe. So that's the biggest kind of multiverse.
And you are deeply unconvinced by all of this.
Well, I think it's kind of interesting to talk about because, like, for example, in this eternal inflation multiverse, presumably there are infinitely many copies of me who do all kinds of interesting things. A lot of them probably have a more interesting life than I do. So that's something you can chat about over a glass of wine or two. But I just don't think it's science. It's interesting maybe for science fiction, and I can understand that people find it interesting. They like to talk about, but it's not something that helps us describe the world that we observe. So I don't think it's science.
Right. So in the many worlds interpretation of quantum physics, it's like new versions of me keep getting created, right? There, I keep like kind of multiplying, so to speak. But of course, I don't know about what the other versions are doing. Now, in a certain sense, isn't that the opposite of beauty? And by the way, we should say, not only is this some physicists, I think, say, this is not just an interpretation of the theory. This is what the theory says. This is the most straightforward reading of the theory, right? So we shouldn't dismiss it casually. On the other hand, isn't this about, well, there's something beautiful about it, I guess. And it gets back to the fact that simplicity may not be the only component of beauty, but I don't know. How does that rate on the beauty scale? Many worlds,
No, it's the same thing that we talked about earlier in regards with the dimensions of string theory. So the thing is that if you look at the central equations of quantum mechanics, they will tell you basically what happens from one moment to the next. So this is what is called the evolution equation. And then you have an additional assumption which says if I measure this system, then this happens, and this is the probability distribution, and that's the second assumption. Now, the many worlds interpretation is what you get if you throw out this measurement assumption. Now, and then you can say, well, that's what the axioms are concerned. It's simpler because you have one axiom less, and because the theory itself is simpler, you have all these other universes.
So do you mean many worlds is what you get if you throw out the assumption that the act of measurement is what is forcing reality to assume definite shape, or
No, you just say that it goes on forever. This time evolution.
Okay.
So you get this branching in all the different universes, but you do not collapse it to one universe.
Right, because the idea with measurement is that when you measure it, you're actually getting the one thing that was actually the case, as opposed to just getting a part of what is actually an internally ramifying kind of picture.
Right, exactly.
So now, I think that there are some cases where you think the quest for deeper explanation or simpler explanation is warranted. And I think one example is dark matter, right? You do think that there's something weird. There's this, there are these various things that lead us to believe that there must be matter out there that we're not seeing. Otherwise, I don't know, maybe the universe wouldn't be expanding at this rate, whatever it is. It's various things, right, that lead us to think there's missing matter. And do you think that's an actual genuine mystery that must have a solution?
Yeah, that's just an incompatibility of the data with the current theories. So there definitely has to be a solution for that. It's a good problem. Let me put it this way. We have, if you only take the standard model and combine it with general relativity, it does not fit on the observation. Mm-hmm. And dark matter is a simple way to make it fit the observation. Another way to make it fit is that you change something about gravity. So this is called modified gravity. Either way, you have to change something about the foundations of physics. And there gotta be a solution to that.
So in your ideal world, how would physicists be redeploying their time and energy? Would there still be like, okay, so a few of them would be working on grand unification. We can afford that. But like, first of all, that's one question. Would there still be some work on supersymmetry and so on? And secondly, like where would we redeploy the intellectual, and financial, for that matter, energy? Where would we redeploy the resources of physics in your ideal world?
You're asking me questions. Well, so one thing is that I really hate getting this question. People ask me all the time, but really the message that I'm trying to get across in the book is please use your own brain. Don't ask other people, come to your own conclusion, and then they come and ask me what to do. And I'm like, okay, so that clearly
I think you should embrace your role as a guru of physics. I think people should make pilgrimages to your office and ask you what they should do. Okay, so I'll give it a try. So first, I want to be really clear. I don't think that any of these approaches should be given up because, they could be right. Like, for example, supersymmetry. Maybe supersymmetry is actually realized somewhere up the Planck scale. Who knows? I do totally understand all the motivations that people have to look at it. What I'm saying in the book is that I wish people would focus on well-defined problems first, because that's where we're most likely to get good experimental results that will help us further develop the theory. Dark matter is an example, right? So we could learn there what kind of particle it is, or if it's not a particle, then it's modified gravity. And that would tell us something new about gravity or the standard model, and then we could build on this and move on from this. But right now we're stuck in this vicious cycle where we're trying to test theories that don't seem to be right, like for the search for unification or supersymmetry, and we're doing all these experiments looking for dark matter particles, and they never find anything. Mm-hmm. And this does not help us developing the theory. So we keep getting, null results, and we go around in this loop all the time. But generally, I don't want to get too specific on the particular topics. I think that would be a mistake. I want people to freely explore their ideas. I think what's really bad is that the current organization of academia so strongly rewards people for working on what is already popular. It makes it so hard to get out of a field if you think it's no longer promising. Like if you have spent, say, the past 20 years working on string theory, even if you come to the conclusion it's no longer promising, what are you going to do? No one else is going to give you a job. So you're basically forced to continue to proclaim it's the most promising thing ever. And that's exactly what we see. Do you want to name names?
No. I've named
we could get a lot more people. We could get a lot more people to watch this if you did, and then more people would know about your book.
I've named names in the books, and I think I've named enough names.
Okay. I got to say, it is an appealing idea. It's like when I think about it, the idea that beneath it all is a single algorithm is an idea that for some reason is so appealing that I tend to think it's true. But that's just an aesthetic judgment in your view that I shouldn't trust.
Well, it really depends on what you mean with a single algorithm. As I already said, we definitely need to get together the standard model with general relativity, right. And that would be a single algorithm. But that doesn't necessarily imply that you also have a unification of the three forces in the standard model. So.
Okay. So final question. We haven't talked about the actual title. We've talked a lot about physics, but the title is Lost in Math. And we haven't talked about the connection between the fact that theoretical physics is a very mathematical enterprise and this like beauty thing, right? So, I mean, for example, when we talk about simplicity, I guess we're talking about mathematical simplicity, right? And I don't know enough advanced math to even know what that looks like. I mean, my conception of mathematical simplicity is like 2 + 2 = 4. That's simple, but that can't be what they mean, right? And yet there is a connection between math and the notion of simplicity, right?
Well, as I already said, I think the way that physicists use the word simplicity is that a theory has very few assumptions. So I don't think it's a complicated criterion if you talk about simplicity.
So it's really not the math itself that needs to be simple.
No, it definitely isn't. Actually, the math is quite complicated, at least for what normal people tend to think about it. For example, if you have one large symmetry group, that's considered simpler than if you have 3 small symmetry groups. Mm-hmm. Right. So that's a concrete example. This is why symmetries help you making things simpler. So, but you are right. So all these criteria from beauty, though I, of course, try to explain them without using mathematics, are actually mathematical criteria, or at least you could write them down as mathematical criteria. And now the reason that the book is called Lost in Math is that I think that these criteria of beauty have gotten lost in math. They are just being used now as mathematical criteria, and no one asked where they originally came from. Like this criterion of technical naturalness is an example. I mean, students today are just taught that there is this criterion and that a theory should fulfill it, but they don't ask, like, why? Where does it come from? Mm-hmm. So that's where the title come from. Okay.
All right. Well, thank you so much. Again, the title is Lost in Math, How Beauty Leads Physics Astray. The title of your blog is Backreaction. That's one word. And are you on Twitter or anything else you want to advertise?
Yes, I'm on Twitter under the name SKDH.
SKDH. Is that... Can you reveal why? I guess is your middle initials DK?
Yeah.
An astute inference on my part. Well, thank you so much. Good luck with the. No, actually, one final question: do you get a sense that you're making some headway? I mean, is this getting serious reception in physics? And people are getting people to talk about it and consider the possibility that you're right.
In the communities that I'm talking about, for all I can tell, no. But I have gotten some pretty good feedback from philosophers and from sociologists, and so I'm in contact with some people, and it's interesting.
Okay, well, good. Well, all insurgencies start small. Well, thank you a lot, Sabine. And good luck with the book.
Thank you.